Hello, we are now continuing the introduction to the Big Data Applications and Analytics course, which is part of the data science curriculum at Indiana University, Bloomington. This last part starts off with a discussion of clouds. And of course, clouds are central to our whole philosophy of this course, which is that when you do anything in this area, you're going to be using clouds. You're going to be running data analytics. You're going to do it in collaboration with lots of people. You're going to process big data, and you're going to solve problems in lots of different areas, which are generically called X-informatics, like bioinformatics or business informatics or wealth informatics or and also you can also refer it to as e-biology or e-chemistry or e-wealth and what have you. So and then of course we have this collage we put together of all these different informatics areas as they're documented on the web. So here we discuss cloud infrastructure. And this first slide, which is dynamically instantiating itself, is probably already out of date. It came from a 2012 talk given by Microsoft, and it points out that a cloud, although it looks like a single entity, is actually like some of these other concepts like grids are made up of lots of parts. The difference is grids expose those different parts, clouds hide those parts, and they provide, in this case, the common Azure interface to any part of the cloud. And they have, as you see here, many data centers of different sizes, with maybe the largest data centers having up to 1 million servers in them, which is quite a lot of servers, bigger than I'm sure your university computer center or probably your company's computer center. And Microsoft says they have around 100 of these centers. And this one here represents some sort of view of the future as to how these centers will be reduced. Because you're doing these things on a totally different scale from before, it makes a lot of difference how you build them, because you want to build them so they're very, very cheap to build, very easy to add resources, very low in power. And so here we have a vision of actually some Microsoft future generation data center, which is sort of open, doesn't waste money on bricks and tops and things, because one key feature of clouds is clouds are already so large they have to worry intensely about fault tolerance. Once you've decided you can cope with faults, then faults don't matter so much. So you can actually afford to build centers which are easier to scale and cheaper to run, but actually might have more faults, because you've already decided faults, as long as they're a reasonable level, don't matter so much. So that's a very important, interesting concept. Here's another slide. This one effectively comes, I think, from Google, although the talk is from, again, Microsoft. It points out some of the reasons for clouds being a good idea. It's just the economy of scale. Namely, we have here, the networking. If you take a large data center, you might be 7 times as efficient in terms of networking costs, 6 times as efficient in storage costs, and 7 times as efficient in administration, because if you have lots of the same thing, you do not need to scale up the system admins proportional to the number of computers. And here we have a nice little picture to show you that these data centers are over 10 times bigger than a football field. So, and here is these big Google data centers. They have up to, I think centers around now typically at tens of megawatts, and they're going to get up to 200 megawatts in the future. And the current CPUs are around 150 watts per CPU. And here we are obviously placing these centers in a place where electrical power is clean and cheap, because that's another interesting feature of clouds. Once you decide you're going to do things remotely, then you don't really care whether it's at your own university or actually sitting um, in a naturally power efficient, easy to maintain place, and so you get green cheap power. These are, of course, reasonably important issues for the future of things like computer centers. If we decide that really it doesn't matter, this may be a mistake to have general purpose computers next to us, then that's a reasonably important deduction. And people often remark that we go through these trends. That's one day computers are centralized, the next day they're distributed, and now what we're going towards a centralized computers. However, we're going to a totally distributed sensor world, with the whole world covered with sensors. That's the Internet of Things with the 75 billion devices by 2020, where they're talking to centralized computers. So we have this interesting difference between the sensors and the computers. Clouds here are the computers, so they're centralized and are likely to remain so for the near future. Uh, this illustrates a little more detail of what we had on an earlier slide, that another important aspect of building these things is to make them modular. And one of the ideas is that the typical shipping rack is a natural unit of computing. And this press release here says that for the Chicago facility, which is now not so new, Microsoft will have a couple of hundred shipping containers, and that's the basic unit. And this is all in efficiency issues. We need to have ideas of scale, and that when you want another 100,000 computers, you just do something very simple. Here's a picture of eBay showing that computers are actually, people often go on tours at computer centers, and they're only impressive by the fact that they never end. And so here we look into a bunch of eBay computers never ending. Of course, eBay has lots of computers, but not as many as Amazon or Google or Microsoft. Here's some comment on greenness, and there is an important thing called the PUE, which is the total facility power over the IT equipment power. So if it was 1, all your power was going into the computers and calculating numbers and storing data. However, if the PUE was 1.8, which is what the average was a couple of years ago, because that's when this slide came from, then if it's 1.8, that says 80, that when you supply 1.8 units of power, 40% of it is wasted. But clouds are much nearer, much more efficient. They only waste about 10 to 20% of the power, with a PUE between 1.1 and 1.2. And I think clouds have actually pioneered the fact that data centers can be made more efficiently. And that's an important result of the cloud initiative. It has pioneered more efficient data centers. I already discussed with you the 4th generation data centers, so that everything is modular and building everything in a very simple, scalable fashion. Scalability is critical. I say we're trading off fault tolerance, we're trading off peak performance of an individual node against scalability, because we're doing horizontal scaling. And we do a lot of processing by taking the data and spreading that data across the computers. We're not making that computer run a lot faster. So that's vertical scaling, is making the individual resource run faster. Horizontal scaling spreads the data across lots and lots of resources. That's the classic Hadoop HDFS style computing. If we look at 2010, there were meant to be 30 million servers worldwide. We have an estimate at the bottom. In 2014, we're going to add 10 million new servers and 10 exabytes of storage in cloud centers. So this number of 30 million is probably no longer correct. These types of numbers are relatively hard to find because places like Microsoft and Google tend to keep them pretty secret, and so does Amazon. They don't want to tell you how many computers they have, because then you could work out how efficient they are and how much money Amazon is making per computer, and then people will make nasty remarks, or maybe they'll be so dazed, it's dazzled, it will be wonderful. But this is a very commercially aggressive world where small differences are very important. Um, so if you look, actually, Google issued some numbers which allow people to sort of reverse engineer the number of servers based on what they said about power. If you looked at this time of 2010, Google was 200 megawatts, which is 1% of the total power, less than 1% of the total power used in data centers. And that actually they're actually 3% of the total compute power. That's because their centers have a PUE around 1, and at this time, the average center had a PUE around 3. So this is just an interesting estimate of size. I'm sure Google has more than 900,000 servers now, as we look from this number of 10 million for the total, for the estimate of what's going to happen in 2014 to 15 in commercial clouds, and that Google will be a significant participator in that 10 million. Here we can actually now look at supercomputers. One of the top supercomputers, it no longer is, it's now a machine in China, is Sequoia at Lawrence Livermore Laboratory in California. Has performance of so-called 16 petaflops, 8 megawatts of power, and it has 1.6 million cores and 1.6 petabytes of memory. So if you compare that with the largest cloud computing centers, they have 100,000 servers, which is roughly the same number of cores. And although as we pointed out in the earlier slides, that they actually now today have 1 million servers. So these cloud centers are at least as large as the largest supercomputers and probably significantly bigger. So if we look at these supercomputers, we have to remember that supercomputers are aimed at individual jobs. Clouds are aimed at all jobs. So clouds are much bigger. But they don't on any one job necessarily get the same performance as supercomputer. Although if you consider Google search as a single job, not something that's quite the way to think about it, Google search is using much more computing power than a single supercomputer, as is Microsoft Search and Yahoo and people like that. So we look at this world. We're seeing numbers, tens of millions. We're seeing totals, 30 to 50 million servers. We're seeing 20, 30% of them, maybe 30% of those in clouds. And supercomputers are, I say here, 1% of the total cloud computing. And of course, supercomputers, and when you add them up, you get quite a big additional factor. So technical computer and supercomputers add up to a reasonable computer power, but they're not as big as today's clouds. Clouds have much more computing than high-performance computing. High-performance computing is critical. It gives you peak performance with closely coupled, highly parallel jobs. Clouds do not do that. Clouds are doing a much different type of computing, which actually tends to be more relevant for data science, where the peak performance is the optimal communication is not quite as necessary and things like that. So these are issues we can discuss later on, but let's just get an idea of where we're talking about. 50 million servers and only 100,000 of them in a single supercomputer. Here we have a well-known chart from NIST, which tells you why clouds are important. They have elasticity. So if you want 1,000 cores, you get 1,000 cores. You don't have to write a purchase order to buy the computers. They're accessible from anyone. They are sitting possibly in this remote, power-efficient place, but they're sitting with broad network access. Resources are pooled. You share clouds. That has important, sort of somewhat negative security issues. And you pay for what you use. You don't, so it's expense that you use it, not as capital, and their whole allocation scheme is highly flexible. And as we pointed out several times in this lesson, there are economies of scale in performance and power. Something we'll discuss later on is the clouds also have amazing new software models. The cloud computing um, initiative is not only produced clouds, it's taught you how to build data centers better. It's produced whole new software models, virtual machines, platform as a service, programming ideas like MapReduce and NoSQL and big data and big table and so on. And these are all important. So clouds, because they're solving bigger problems than anybody ever solved before, have produced huge amounts of innovation. So now that's our finish of our overview of cloud computing, which underlies all of this class, and we'll move on to more features of the data deluge. Thank you very much.